Hello everyone, I'm Kaiji Wei from Department of Information and Computer Science in Keio University. Today we would like to talk something about the neural network implementation methodology on a low-end FPGA board. Well, let's get started with our introduction. First, I want to make clear our motivation for this research. As you know, the AI technology is facing an unprecedented revolution, including the application model, performance, or even efficiency. Various kinds of the platform have been applied in different research areas. Among these, platforms like the GPU, clouds, and FPGAs have been the three most popular ones. These platforms are faced with the trade-off between the flexibility and efficiency. I would like to remind that most of these platforms are power-hungry devices. However, as you see, the mobile devices embedded with AI system, something like the Siri in iPhone and autonomous driving car, have been required by people recently. However, these power-hungry devices fail to meet these industrial demands, so FPGAs strike out from all of these rivals. Considering the evolution of neural network model, a much more swift development tool which can adapt to various target devices is expected. This is one of the reasons for us to choose HLS as our development tool. According to the report from Xilinx, HLS can also achieve a comparable performance with the least development time period, comparing with HDL. As you can notice from the design data flow, HLS is much more accessible to the software engineers. However, it cannot be denied that it is hard to inspect the implementation detail on hardware, while HDL can perfectly make up such kind of deficiency. Although we don't need to write HDL code when running HLS design data flow. Hardware-efficient C implementations are necessary to achieve the best performance. After designing the design tool, it's time for us to go across the target board and our benchmark. The following experiments are all based on these two targets. Regarding the target board, we choose a low-end FPGA device, PinkZ1, which can directly confront the circumstance of the resource deficiency. As noticed from the table here, the resource available on PinkZ1 is far less than requirements in implementing the neural network model, referring to some previous researches. Talking about the target model, we would like to mention that YOLO v3 is one of the most high-performance network models. The original design consists of the 53 layers with these 5 different variations. With considering the platform, the tiny one, YOLO version 3 Tiny, seems to be much more suitable for our research. It runs roughly 4 times faster than its larger brother in a much more compact model size. And as part, I would like to go over the components in convolution neural network model. First, convolutional operation. A filter slides over an input feature map, performing an element-wise multiplication with the part of the import, and then summing up the results into a single output pixel. As the picture shown here, we can get the basic idea of the convolution neural network. And then, following the convolution operation, we use the batch normalization to enable a faster and stable training with these 4 formulas shown here. Besides, activation function determines output of the network model with different algorithms based on the desire or the property of the neural network model. Finally, the pooling layer are used to subsampling to reduce the spatial size of the representation. Well, we have finished the introduction of the neural network components. From this part, I would like to introduce the two key techniques applied on a model comparison. One is model pruning. Generally, the algorithm is divided into these three parts, and the model input with the selected objective. With different objectives, we may change our pruning techniques, as we show in the relationship here. And pruning includes three levels. One is the pruning level determination, which is just connect to the objective or the purpose of our pruning, as I have described previously. Then, the pruning criteria just describe the relationship or the connection between two elements. Finally, the pruning algorithm, which is the kernel part to prune a model. And when we move on to tuning step, the model goes through the fine-tuning, evaluation, decision-making, these three steps recurrently until it can meet expectation of the developer. The other techniques we would like to introduce is the model binarization. To simplify our explanation, we can just understand the model as the mechanism to change the neural into 0 and 1. Besides, the convolution operation can also be simplified into XNOR bit counts, which can greatly relieve the burden of the computation intensity. Later we will expand this algorithm in detail, so we're gonna skip this part shortly. Okay, after knowing the general idea of our research, I would like to point out three difficulties exist in our implementation. First, the requirement of significant storage and computational resources. Then, different components of a neural network model have to be implemented into different modules. Finally, considering the resource utilization and speed, a proper resource usage mechanism should also be proposed. In our proposed frameworks, it is divided into three separate stages. Import stage, with some pre-operations to serve the later optimization. Algorithm level downscaling, which includes the model pruning and the model binarization. Finally, the hardware optimization is to adapt the trained model onto the specified board with different techniques. During the second stage, we struggled with the mean average procession and model size, while the later stage is the rival between the performance and the resource utilization. The following introduction is around the later two parts. Well, before talking about the model pruning, I have to point out that during the pre-operation of the model, we substitute the original key REU with the LEU function to reduce the computational intensity of the whole model. In selecting the algorithm, since you would like to reduce the memory capacity of the whole model, channel pruning should be a better choice. The rest of the algorithm is set in this way, including the pruning criteria, pruning algorithm, and fine-tuning. According to the research proposed by Liu, we summarize our pruning function into L to prune the channel of our model efficiently. Then we would like to introduce the algorithm of the model binarization and the forward propagation. Comparing with the conventional model, the weights are constrained between -1 and +1. Regarding the activation function, instead of using the stochastic function, we choose the deterministic function with considering the later hardware implementation. Then, in the backward propagation, we keep the real value weights when using the gradient descent-based method, SGD. In this way, real value can be updated as well as the gradient descent. Okay, we have finished the algorithm level downscaling. Next, we want to move on our discussion about the hardware optimization. In this page, let's talk about the hardware implementation of the convolution level. As mentioned previously, the convolutional operation in binarized neural network is realized as XNOR bit count operation. In a processing element, the data works in this way. Pop count operation is implemented. The operation of counting the number of set bits. Both feature map and the kernel are expanded into column vectors to increase the computational efficiency. In addition, to decrease the latency, both inter-level and intra-level pipeline are conducted on the data stream. Conventionally, the feature map's dimension and kernel dimension are quite different. If we transform these metrics into data stream, we need to load almost the whole feature map, which may again challenge the results on board. Since the addition is just an operation of pop count, as long as the vectors corresponding to the unrolling order in the kernel, the order of the column will not affect the output result. Here we show the data flow on board. To further clarify our implementation, while in the hardware design of the pooling layer, we prepare a two-line buffer with the same size as we shown here. We first compare the element in the buffer with the same index. The larger one is the retained for the next stage. The index is increased by 2. Then, we compare the adjacent to result. From the previous stage, the larger one is the result of the pooling size of 4. Besides, we also show the data flow of the pooling module here. Regarding the batch normalization, although it seems to be a computational intensive operation, especially on DSP, in binarized model, we don't need to worry about that. Since activation function, we choose to be the deterministic function. The result is determined by comparing the input result with threshold. The complex algorithm implementation of hardware can easily be simplified. Finally, we would like to present the whole hardware architecture. Since the input layer and the output layer are not binarized, the convolutional operation of the input layer works on the PS part. On the PL part, the AXI controller is used to control the data stream on board. During the implementation, we encounter with the problem of LUT shortage. As a strategy, we move part of the LUT calculation from LUT to DSP, with returning the binarized data to 16-bit floating point, instead of the original 62-bit ones, so that the model can embed it into PINX-Z1 successfully. Till now, we have finished the introduction of the frameworks. Following, we're going to evaluate our frameworks in previous 2 stages respectively. Our training works on the Cocoa dataset, which is constrained to 8 classes, and it is performed on Tester P100. In the algorithm level downscaling, which includes pruning and binarization. With the pruning algorithm adopted, 82.5 parameters are pruned, and the model size is decreased around 85%. Because of the compact model size, the inference time reached 2 times faster than input model. And there is just a slight increase on MAP performance. However, what a shame is that during the fine-tuning, it doesn't show any improvement on the model. And from the graph we shown here, we just summarized the mean average precession, intersection of union, and the reduced model size, which evaluated on different techniques we have applied on the model, such as the RUU substitution, pruning, fine-tuning, and the binarization. Comparing with the benchmark ULO version 3, the model of the whole architecture is reduced by 97% at the cost of 5% of the MAP and 9% of the IOU. During the hardware optimization, I've mentioned that we have once transferred the LUT operation into DSP. According to the generated report from HLS, we relieve 37.2% of resource on LUT and result in the utilization of DSP by 15% eventually. The resource utilization of the whole system presents in this graph. As you can notice from this graph, we have made full use of the BRAN and the LUT in our design. Finally, we evaluate the execution time and the power efficiency upon the ULO model running on our framework. The result application consists of the input layer, hidden layer, and output layer. Since the input layer and output layer run on PS part, thus it's reasonable to set these two circumstances as the same when we evaluate the input layer and the output layer. What we should take into account is the hidden layer. As a result, our design runs 22 times faster than it purely running on ARM core, which embedded on pin Z1. Then it comes to the power efficiency evaluation. We compare our work with the model runs on Xeon. Although we disadvantage on the FPS performance. When it comes to the power efficiency part, our design performs 3 times better than the model running on CPU Xeon. In addition, our work is also comparable to some similar work which realized the neural network on the low-end FPGA board, like FPGA ConvNet or CMP. Although they didn't mention the loss of their accuracy on the model, our design performs 3 times better than FPGA ConvNet and 7 times better than CMP on the instructional performance. In conclusion, we would like to highlight the contribution of our research. First, it is an attempt to directly confront the demands and the deficiency of today's AI applications. To compact the original model, we organically combined the network model with the binarized neural network. In a case study, ULO version 3, the network architecture has been greatly downscaled at the slight sacrifice of the accuracy of MAP. Through the pipelining of the data stream, the FPGA part is accelerated about 22 times than it purely running on the ARM core. Talking about the power efficiency, comparing with the CPU Xeon, it also achieves 3 times better performance. In the future, we will apply our model on another board to prove the flexibility of our design. That's the end of our presentation. Thank you for listening.